Good morning to one and all present over here. Today we will see about sprue part 3. So coming on to angulation of a sprue former, so it should never be directed towards thin, delicate cross section of the wax pattern. It should be directed away from or at 45 degrees to these details. It should never be directed at right angles to a flat portion of a wax pattern. So what happens is that if it is being directed at 90 degrees, it creates reverse flow with turbulence of the melt, decreasing melt's ability to fill the mold. And melt increase a 90 degree to a flat wall or floor can create a concavity in the wall opposite to the sprue, and which in turn creates a convexity in the restoration. So this is how it should be present. So when it is being presented at 90 degrees, it causes maximum impedance to flow when a sprue former is added 90 degrees to the pattern. So coming on to reservoir, it is a small amount of additional wax which is being added to a sprue former 1 to 2 mm below the wax pattern. It has dimensions far exceeding the thickest portion of the wax pattern, and it should be indicated in cases of longer or thin sprue, and any other reason that might cause the alteration of flow of the metal can require a reservoir. So function of it is to compensate for the shrinkage which occurs during solidification of the casting. So coming on to two types of sprueing, direct and indirect sprueing. So direct sprueing is one where a sprue former provides direct connection between the pattern and the crucible former, and a basic weakness of direct sprueing is the potential for suckback porosity which occurs at the junction of restoration and the sprue. So coming on to indirect sprueing, molten alloy does not flow directly from the casting crucible into the pattern area. Instead, the alloy takes an indirect route. The connector or the runner or reservoir bar is often used to which the wax pattern or the sprue formers are being attached. So this is called as a connector or reservoir or runner bar. So indirect sprueing offers advantages such as greater reliability and predictability in casting, plus enhanced control of solidification shrinkage. So the parts of it include part 1 is the feeder sprue, and 2 is the horizontal running bar, and 3 is the manifold sprue. Basically, we have three sprue designs. So there is a conical sprue, there is a bottleneck sprue design, and there is a cylindrical sprue. Coming on to vents, additional sprues placed at thin or thick wax patterns to improve the quality of the casting is called as vents. These are examples of vents. So coming on to casting defects related to sprue, we have localized shrinkage porosity, suckback porosity, and incomplete casting. So coming on to localized shrinkage porosity, which is also called as shrink spot porosity. So it is being caused by premature termination of the flow of molten metal during solidification or incorrect sequence of cooling. Usually, a sprue should freeze at last. If it freezes before the rest of the casting, it will lead to porosity. So ideally, the molten alloy located farthest from the sprue button should freeze first. So this should be the first to freeze and the sprue should be the last to freeze. So the metal on solidification shrinks. The linear contraction of noble metal alloys in changing from a liquid to a solid is at least 1.25%. Therefore, continual feeding of molten metal through the sprue must occur to make up for the shrinkage of metal volume during solidification. If the sprue freezes in its cross-section before this feeding is completed to the casting proper, a localized shrinkage void will occur in the last portion of the casting that solidifies. So the porosity in the pontic area, that is the ability of the pontic to retain heat because of its bulk and because it was located in the center of the ring. This problem can be solved by attaching one or more small gauge sprues, that is 18 gauge sprue, at the surface most distant from the main sprue attachment and extending the sprues laterally within 5 mm of the edge of the spring. So we can have additional sprues like this. Okay. So these small chill set or auxiliary sprues ensure that solidification begins within the sprue and they act as cooling pins to carry away heat from the pontic. So generally this localized shrinkage porosity occurs near the sprue casting junction. It can be prevented by using sprue of correct thickness, decreasing the length of the sprue, attaching the sprue to the thickest portion of the wax pattern, flaring the sprue at the point of attachment and placing the reservoir close to the wax pattern. So coming on to suckback porosity, it is an external void seen in the interior of the crown near the area of the sprue if a hotspot is being created. So this is called as a suckback porosity. It often occurs in the occlusive axial or incisive axial line angle that is not well rounded. The entering metal impinges on the mold surface at this point and creates a higher localized mold temperature in this region, which is called as hotspot. So hotspot may retain a localized pool of molten metal after other areas of casting have solidified. That is, it causes the local region to freeze last, resulting in suckback porosity. It can be eliminated by flaring the point of attachment, sprue attachment, and reducing the temperature, mold mill temperature. So coming on to conclusion, thus sprue plays an important role as a channel in replicating the finer details as in wax pattern. All the requirements of the sprue should be met to produce a proper casting. So these are references.